So we'll discuss about 2D collision, and before that, just a bit of revision about uh, 1D collision, 1D collision, and the coefficient of restitution. The coefficient of restitution, E. It happens to be velocity of separation divided by velocity of approach. That means if the bodies, say M1 and M2, having velocities U1 and U2 before, and afterwards, after collision, they have velocities V1 and V2. So as per this diagram, velocity of separation is V2 minus V1 and velocity of approach is U1 minus U2. So this is coefficient of restitution. But actually, how is coefficient of restitution defined? That is, in every collision, there are stages just about to make contact to the stage of maximum deformation. This one, the maximum deformation stage. That happens when both the bodies have same velocities, and this is U1 and U2. Just the contact begins, and the last diagram is just the contact has lost. Okay, so here contact begins, and here contact lost, and that is the maximum deformation stage. And this contact begins to maximum deformation stage. This is the stage of deformation, and the maximum deformation stage to the point where the contact is lost, this is known as reformation. Here the shape of the body is regained partly or fully, depends on the type of collision. If it is perfectly elastic collision, then the whole of the shape is regained, and if it is partly elastic, a fraction of the shape is regained by while it carries some permanent deformation. However, so there so masses M1, M2. Now you know the impulses act along which lines here. So impulse, so this line, right? This red line, that is a common normal. See, this red line is along the common normal. So this is known as the line of impact. That means the impulses act along this line. See the impulse here, this way, and here it is this way. Impulses act along this line. However, so here is JD. JD is the impulse of deformation, and JR is the impulse of reformation. So JD plus JR is the total impulse during collision, the impulse during collision. Okay, so what is JD equal to? Suppose you consider this block 2 only, I mean body 2. So JD happens to be M2 times V2 minus sorry, JR equal to M2 into V2 minus V. V is the common velocity, that means during the stage of maximum deformation against this. Both the bodies have equal velocities V each. So JR is this, and JD is M2 into V minus U2. And actually coefficient of restitution is defined like this. It is JR by JD, impulse of reformation by impulse of deformation. So for perfectly elastic collision, E equal to 1. Perfectly inelastic collision, E equal to 0. Partly elastic, E varies from 0 to 1. Okay, so that is about 1D collision. So what is the total impulse? Actually, total is, say, if you consider on the body 2, the body of mass M2, it's V2 minus U2. Okay. So E is the ratio of impulses. Right. Now we'll go ahead with two-dimensional collisions, 2D collisions. In 2D collisions, so 1D collision is also known as head-on collision. So this we are talking about 2D collision. Say these are the two bodies. And this is 2D collision of smooth bodies. So there the two bodies collide, and say the two bodies before collision, just before collision, they were having velocities this. One is having velocity this, and the other was having velocity, say, this one. So here, which is the line of impact? Can you say for these two bodies, these two colliding bodies, which is the line of impact? See, they are smooth bodies, no friction. The line of impact means the line along which the impulses act. That is the common normal. If they are spherical bodies, join the centers. Not spherical, just so that's actually the common normal. Here it's a special case. The bodies are cylinders or spheres. So this becomes the line of impact, the line along which the impulses act. And these velocities before collision, these are the components of velocities. See, the line of impact is the x-axis. Now this velocity was u1 and u2. So that is u1 x, this is u2 x, and that is u1 y and u2 y. Now the impulses act along, obviously, the line of impact. This red arrow shows the impulses acting on the two bodies. Now, what is going to happen after the impact? This is just before the impact. We draw the line of impact. That is the x-axis itself. Now, after the impact, just after the impact, these two velocities will change. So this will become v1 v1x final velocity, and this will become v2x. Now these components will not change. u1y and u2y will not change. Why that will not change? Because, so let me draw this at the final velocities v1 and v2 after collision. Whatever be the directions, that need not be the actual direction which happened to be before the collision. It may be like this. Okay. So this is v1 and v2. So however, whatever velocities change are along the line of impact. The velocity components perpendicular to the line of impact do not change because there is no impulse in that. Perpendicular to the line of impact means y-axis. So along the y-axis, there is no impulse, so no change. So therefore, this velocity component, see u1y and u2y, they remain even after the collision. So which all velocities changed at this? U1x, U2x, changed to V1x and V2x. So dealing with a 2D collision is pretty much simple. That's just mass M1, M2. So just deal with the x-axis and forget about the y-axis. Nothing changes along y-axis. So it's simple as that. M1 U1x plus M2 U2x equal to M1 V1x plus M2 V2x. Now E is along the line of impact, right? Because E is the ratio of the impulses. It has nothing to do with y-axis. So that is V2x minus V1x divided by U1x minus V2x. So here E is velocity of separation divided by velocity of approach, but along the line of impact. Along the line of impact. Okay. So what's the line of impact? Line of impact is the common normal. That means if their bat and the ball, they hit, the ball hits the bat. Obviously, this is the line of impact. Okay. It varies. It's just the common normal. Say an inclined plane and a ball there. A ball and the inclined plane collide. Obviously, this is the line. The common normal between the ball and the incline. But at the region of contact, common normal drawn is the line. Okay. So, there was a result in 1D collision where, this result in 1D collision was there, say, in 1D collision of bodies of equal mass and also elastic collision, that is equal to 1, the bodies exchange velocities. Bodies exchange velocities after collision. This was for 1D collision. Now, in 2D collision, there will be a problem like this, that consider uh, oblique collision, or that means 2D collision. Consider oblique collision of two bodies of same mass. One of them at rest before impact. Prove that after impact bodies move at an angle of 90 degrees. That means the final velocity vectors make an angle 90 degrees. It is perfectly elastic collision, oblique collision. Oh, I have not written that. No? Consider perfectly elastic only in that case. A special case. Consider perfectly elastic oblique collision of two bodies of same mass. One of them at rest before impact. Prove that after impact bodies move at an angle of 90 degrees. So we'll consider two bodies. This one. Now this body was at rest. This body was at rest before. Another body was moving towards this body. but both have same mass. So this was moving, say, with a velocity this v. Now, to prove that after impact, they will move at right angles. Now, here, which is the line of impact, here, line of impact. Now, let us draw the after collision. What happens after collision for this one more diagram. Now, suppose this angle happens to be theta. So this velocity vector, this component is v sine theta, and this component is v cos theta. Now, after the impact, this v sine theta will remain as it was because it is perpendicular to the line of impact. So, and no impulse act along this perpendicular to line of impact. So, along the line of impact, the bodies will exchange their velocities. So, bodies will exchange their velocities. So, whichever was, I am talking about the line of impact, whichever was having velocity v cos theta, that will come to rest. So, come to rest means come to rest along this line of impact. Whichever was at rest, that will gain a velocity of v cos theta. So we have made use of that result. 1D collision of bodies of equal mass, bodies exchange velocity. Along the line of impact, it is like 1D collision. So if you forget about whatever happens in this y-axis perpendicular to the line of impact, because nothing will change in that direction perpendicular to the line of impact. So this proves that the bodies, obviously you can see from the diagram that the bodies move at an angle 90 degrees. So now we have learned that when a ball hits the ground due to collision with a massive body, that means when the ball hits the ground with velocity v, the coefficient of restitution is e, then ball comes back with velocity ev, because ground is not going to move, or it is collision between the ball and the earth. So the ground is actually earth, no? So the earth also moves a bit, but that too is very much negligible. So this is the, so just before impact, and this is after impact. So this is when a ball drops in vertically. The ball drops vertically, right? Just released from a certain height. Say this ball drops vertically. Now it bounces off with the speed ev after impact. It will go to a lesser height uh, than from where it was released. Now, this is, you can think about the oblique impact. Say a ball, this is just when it hits, suppose the ball comes along this particular line. Okay. And it makes an angle theta. It makes an angle theta. And that normal is obviously the line of impact. This is the line of impact. So now, suppose the ball comes with a velocity v. So that's before impact, ball has velocity v. So it has the components that's v sine theta parallel to line of impact and v cos theta perpendicular. So now, after impact, what is going to happen? This v sine theta is not going to change, while see, along the line of impact, it will bounce up at a with a velocity ev cos theta, because You know that velocity of separation by that of approach is E for the velocity components along the line of impact. So now the ball moves, making a certain angle, theta dash. So what is theta dash? So from the diagram, tan of theta dash, so you can form a vector triangle. Like this. Say final velocity is v dash. So v dash is vector sum of this ev cos theta, and you can draw the vector upward here to apply triangle law, v sine theta, and that's theta dash. Tan of theta dash from this diagram, tan of theta dash is equal to v sine theta divided by ev cos theta. So that means tan of theta dash is equal to tan theta divided by E. So that is tan theta divided by E. For elastic collision, what will happen? For elastic collision, perfectly elastic collision, E is equal to 1, then E equal to 1. That means tan theta dash is equal to tan theta, so theta dash equal to theta. So it gets reflected, I mean, like light gets reflected. So it's like following the law of reflection of light. So if collision happens between a body and a certain surface or say ground, it will follow this, the law of reflection of light. Comes at an angle theta with normal and goes back, bounces off, making the same angle with the normal.